Hi everyone. In this video, we are going to go over the answer key for problem set 10. Problem set 10 combines the information we have been learning about hypothesis testing up until this point. In problem set 8, we covered one sample hypothesis testing, and in problem set 9, we covered two sample hypothesis testing. Now here in this problem set, we have to first make the decision about what type of hypothesis testing we're going to complete, whether that's one sample or two sample, or for means or for proportions. And so keep that in mind as we're going through each of these questions here today, because that's the first decision point we have to make. So as we're reading through these problems, the first thing I'm going to keep in mind, and what you should be keeping in mind as well, is what type of test are we conducting? Because we know that's going to affect our very first step, which is assumptions, because those vary depending on what type of test we're conducting. And so with that being said, let's start off with question number 1. The average probation officer caseload nationally is 97 clients with a population standard deviation of 22. A random sample of 75 probation officers from Iowa shows an average caseload of 91. Is there enough evidence to suggest that the average caseload in Iowa is significantly different than the national average at an alpha level of 0.05? You must complete the 5-step model of hypothesis testing and show your work to receive full credit. Please round your z obtained value to the hundredth place. Okay, so as I mentioned, the first decision we have to make is what type of test we are conducting. As you see here, I have highlighted in yellow, so we're not really hiding it here, is that we are conducting a one sample test for means. But let's go back to the problem itself and the language that's used within it to figure out how we know that that's the test we are going to be conducting. And so right off the bat, the second word I see here is average. The average probation officer caseload. And so right away, that should trigger for you, I am going to be conducting a test related to means, because we know that means and average are synonyms, they're interrelated terms. And so rather than proportions, we're going to be using means. And so the next decision point is just, am I going to be doing this in a one sample context or a two sample context? So let's keep reading along. The average probation officer caseload nationally is 97 clients with a population standard deviation of 22. And so one of our keywords to signal a grand population is nationally. And I also see with a population standard deviation of 22. So that's signaling to me that we're comparing probably one distinct group versus an entire population. And so I see here in the second sentence that we have a random sample of 75 probation officers from Iowa that shows an average caseload of 91. And then our question itself is saying, is there enough evidence to suggest that the average caseload in Iowa is significantly different than the national average in an alpha level of 0.05? And so you can always refer to this actual question itself. This is essentially our research question here to really get a solid look at what type of test we'd be conducting. We have our keyword average here, and we can see that we have our first group here of Iowa, and we are comparing that to our national average. So it's one group versus the entire population, meaning the national average. So that's how I know we are conducting a one sample test for means. So before we even get started with the 5-step model, we have to figure that out, right? And so with that being said, let's dive into our 5-step model approach for this. Step 1 is always stating our assumptions. And like I had mentioned before, these assumptions change based on what test we are conducting. And so that's why we have to figure out this part first. And so the 3 assumptions we make for a one sample test for means are the following. First, we are working with an independent random sample. Again, think of your assumptions as your checklist here, right? We have to verify that all of these 3 things are met in order to move on to the subsequent steps. So I see here that we do have a random independent sample here. So we're good on that. The variable we are testing is interval ratio. So let's take a look here. We see here that a caseload is within a count, so it's a numeric number. In terms of caseloads, we know that a caseload is an individual count, so it would be 97, 98, 99, right? We can measure that in between, and it has a set scale, so we're good on that as well. And then lastly, we just want to ensure that our sample size for our group, or our sample in this case, exceeds a value of 50. And so we need to go to our sample itself, and I see that our random sample is of 75 probation officers. So because of this, we have exceeded our 50 threshold, so we can assume that our sampling distribution will be normal. Importantly here for this assumption, what I've seen with a lot of folks at this step with assumptions is that you're either just stating this component here, you're just writing, that 75 exceeds 50 or is greater than 50, or you're just saying normal or normal distribution. The key with this assumption is both components have to be necessary, right? It's because n exceeds 50 that the sampling distribution will be normal. Both of those components have to be present for us to check this one off. If you just say that the sample size exceeds 50, that doesn't actually satisfy this assumption. And so please make sure that both of these elements are listed. Essentially, you can just copy and paste this one right here. There's no reason to reinvent the wheel. This is what you should have written down, both that the sample size exceeds 50, and because of that, the sampling distribution will be normal. Okay, we've satisfied that as well. So now we know we can proceed with step number 2. Our hypotheses. Okay. Always make sure that we have these written in statistical notation. So starting off, I know that my null hypothesis will always start with H in a subscript of 0, and my research or alternative hypothesis with an H1 or an HA with a subscript. Knowing that we are working with means, I have one of two options at any point with our population parameters. And so, knowing that I'm working with means, I know that my symbol designation here is going to be mu. Now, if we were working with proportions, this would be the pi symbol. But because it's means, that's our only option here, right? And we'll get to proportions just in a little bit, but this is our only option when we are working with means. And because this is a one sample test, we want our population parameter here to equal what our national population parameter is. So in this case, it is 97, right? 97 clients is the national caseload here. That's right at the top. So let's see here. That's what we have written here. A mistake that I saw a few times is people wrote that it was against 91. Keep in mind that that is actually going to be down here. That's our sample average here. We'll use that within our calculation down here when we compute our test statistic, but that's not what we're testing against. So keep in mind that mu is always our population parameter for means, and so it will always be that national level here. Other key here for our research hypothesis or alternative hypothesis, and keep in mind I'll beat this one over the head because our null hypothesis, remember, is always our statement of no difference, so we're always going to have our equal sign here. But our second decision as well for our alternative hypothesis is what symbol are we going to have here? Is it going to be a less than, a greater than, or a not equal to sign? And to figure that out, we have to revisit the problem itself to see what language is utilized in the research question. So I see that that was in the third sentence here, so I'm just going to reread it to double check. Is there enough evidence to suggest that the average caseload in Iowa is significantly different than the national average at an alpha level of 0.05? My keyword here is different. What that signals to me is that we are not specifying a direction either way of what we are interested in testing. So it's a two-tailed test. It could be lower than, or it could be greater than. Both ends of our normal distribution are in play. And so because of that, we use the not equal to sign. And so keep that in mind when stating your hypotheses. And because of that, now we can move on to step 3. which helps us a little bit because we already just mentioned that this is going to be a two-tailed test. We know that we're going to complete a z-test because it is a one sample test for means. But our main step here is determining where our z-critical cutoff points are. Because we know we are conducting a two-tailed test because we have our keyword of difference here up in step 2, we just have to reference back in our question what alpha level we would be working with. I see here that it's listed as 0.05. Again, I will always provide that alpha level for you. You can go and reference on the slide chart that I have provided to you what the corresponding z-critical value is for an alpha cutoff level for a two-tailed test of 0.05, and that is 1.96 plus or minus, right? It's a two-tailed test, so we're accounting for both the positive end of the distribution and the negative end of the distribution. And so that's really important here to recognize as well. It's not one or the other, it's both. So we have to have this plus or minus sign here. All right, let's move on to step number 4, computing our test statistic. I always like to write out what information I need from the problem itself to solve it based on my base formula here. So I know for a one sample test for means that I need my sample average, my population average, the standard deviation for the population, and my sample size as well. And so with that being said, I can revisit the question itself and pull all of this information out. I know that my sample average was 91, so average caseload from Iowa was 91. Our national average was 97. Our population standard deviation was 22. And lastly, our random sample from Iowa was 75 probation officers. So those are the 4 pieces of numerical information that we need in order to work through our computation step. This is a really important aspect of step 4. What I've seen a lot of the times over the last 3 problem sets, so 8, 9, and 10, is folks will just do this step here and then jump here. What can happen is if you make a calculation miscalculation, I should say, from here to here, there's no real way that I can figure out where that miscalculation occurred, right? If you set it up correctly here, but did not come up with this answer here, I don't know where that occurred. So if you could please show the rest of your work area and how you actually worked through the problem, it's a lot easier for me to identify where those errors occurred, and I can point those out to you a lot easier in my in-text comments, and we can solve that issue a little bit easier. So please show how you're working through each of those steps as you go through those. So this is me working through each of those steps. And you should get a z obtained of approximately negative 2.36. Once we have our z obtained value, we can now make a decision and interpret the results within the context of the problem. Again, I always like to plot out my results. It's easier for me to just visualize this in reference to our normal curve. And so I see that my z obtained value is negative 2.36. From step 3, we knew that this was a two-tailed test, and our z-critical value was both plus and minus 1.96. So because of that, our z obtained fell into our rejection zone over here. So we're out of our safety zone, so we're going to reject the null hypothesis. But the key of step 5 is to always interpret our answer within the context of the problem. If you just say, reject the null, that is not going far enough for the purposes of this question. Essentially, what we have to think of this as is if we were being asked this question on behalf of, an Iowa court administrator's office or something, and we reported back that we are just rejecting the null hypothesis, they don't know what to do with that information, right? We have to contextualize what our findings actually are. And so what we can say, given our results here, is that given that our z obtained of negative 2.36 falls beyond our critical region of plus or minus 1.96, we reject the null hypothesis and conclude, so this is where we're getting into the context portion here, that the average caseload in Iowa is significantly different than the national average. And so the court administrator's office could then, make changes based on that. Importantly, here as well, I've seen quite a few folks have these separated. So they'll say, like, reject the null up here, or even sometimes in step 4. Please ensure that your final interpretation has both of these elements contained in your final response. So you're stating both that you either fail to reject or reject the null hypothesis, and what your interpretation is within the context of the problem, all within one full statement. Otherwise, it can get a little bit disjointed. So please make sure to try and both make that decision and interpret the results all in one here for step 5. Okay, let's go on to question number 2. The state of Illinois wants to examine whether participation in drug treatment courts reduces recidivism. Among 275 individuals who participated in drug treatment courts, 60 reoffended within 1 year. Among 325 individuals processed through the traditional court system, 88 reoffended within 1 year. Is there sufficient evidence that drug treatment courts reduce recidivism compared with traditional courts at an alpha level of 0.01? You must complete the 5-step model of hypothesis testing and show your work to receive full credit. Please round your Z obtained value to the 100th place. So just as we did with question number 1, our first key thing that we have to accomplish here is determining what type of test we need to conduct. Right? We're not going to figure that out on the quiz. I'm not going to tell you what type of test it is. You also weren't given that information on this problem set. And so that's our first key decision that we need to make. So let's take a look at this problem and figure out how we knew it was going to be a 2-sample hypothesis test for proportions. So right off the bat here in the second sentence, I see that among 275 individuals who participated in drug treatment courts, 60 reoffended within 1 year. So what that's telling me is that I could probably create a proportion fairly easily out of those two numbers, right? I could do 60 divided by 275 to get a proportion of those that did reoffend out of that treatment group. Here, I see that there's another group at play, right? I see those who participated in drug treatment courts, and then I have another group here, which is those who went through the traditional court system. And so already, just with this second and third sentence here, I see 2 distinct groups, those that were in drug treatment courts and those that were in the traditional court system. So I already have in mind, right, that I could create a proportion value out of this and that I have my 2 groups. And so with just those couple of sentences there, I know that I'm conducting a 2-sample hypothesis test for proportions, but we can always double check with our actual research question here what we would be conducting. So let me read this third sentence one more time. Among 325 individuals processed through the traditional court system, 88 reoffended within 1 year. Is there sufficient evidence that drug treatment courts reduce recidivism compared with traditional courts at an alpha level of 0.01? You must complete the 5-step model of hypothesis testing and show your work to receive full credit. Please round your Z obtained value to the 100th place. Okay, so we got to the end here. I didn't see anything that would be recognizable in terms of a mean or an average, and I'm left with just 4 numbers here. I have 2 distinct groups, and I know that I could convert these easily into proportions, and so that's how I know that this is the type of test I will be conducting. Again, it's important for us to establish this right off the bat because step 1 is contingent on that, right? Our assumptions are going to be different depending on what type of test we're going to conduct. And so for a 2-sample hypothesis test for proportions, here are the following conditions or assumptions we have to make in order to proceed with the rest of the steps. The first is that we are working with independent random samples. Okay. Here, we need to make sure that they're independent of one another because we don't want to have individuals who both participated in drug treatment courts and traditional court systems. And here I see that they are distinct from one another. And so we're good on that. There's no overlap between our random samples. Second is that the variable we are testing is nominal. Okay, let's go back and make sure that the variable itself we have here is nominal. So we have those who participated in drug treatment courts and those that didn't, or rather the traditional court system. And so here, think all the way back to chapter 1 and 2, I see that this is basically a yes or no question, right? Did you participate in drug treatment courts or did you participate in the traditional system, right? There's no numerical value there. It's basically just a yes, no binary variable. Did you or did you not? And so we can check this one off as well. We're good to go. And lastly, we just want to ensure that both of our sample sizes here exceed a value of 50. My first group here is 275, so we're good to go. And my second group is 325, so we are good to go there as well. Again, as I had mentioned in question 1, please ensure that you have both of these elements listed here. So because our first group exceeds a value of 50 and our second group exceeds a sample size of greater than 50, the sampling distribution will be normal. Both of these have to be there for this assumption to be met. You have to write both of these. If you just wrote that 275 is greater than 50 and 325 is greater than 50, you probably received partial credit, but the point of this assumption is because those things occur, the sampling distribution will be normal. So that element has to actually be written out. That has to be present because that's really the key here of this assumption is that we have to satisfy that issue of normality in order to proceed with the subsequent steps. Okay, let's move on to step number 2, hypotheses. All right, starting off with our null hypothesis or our statement of no difference. Here, we always have our H0 to designate our null hypothesis in statistical notation. And here you will see that our symbol has changed for our statistical notation because now we are working with proportions. An error that I've seen on many problem sets in both problem set 8, 9, and even 10 is that folks are still using P rather than our population parameter of pi to designate their symbols here. We will never use P or small p for proportions at this stage. You will use that in your computation step here because that has to deal with samples. But keep in mind for our hypotheses, we are always testing that against a population parameter. And because of that, we will always have a pi symbol when you're doing a hypothesis test for proportions. And so just get that out of your head. Anytime you're doing a hypothesis test, it'll either be mu, which you just saw in question number 1 for means, or this pi symbol you see here in question 2 for proportions. It's one or the other. It's a binary choice. Write that down if you haven't already or you're having trouble with it. There's no other option. Here, since this is a 2-sample test, we are just signifying here that we're testing one group versus the next group. And so here, we just have a subscript of 1 to say essentially group 1, right? The proportion of group 1 is equal to the proportion of group 2. Secondly, we need to just revisit what our question here is specifying to figure out what symbol we will be utilizing. Is it greater than, less than, or not equal to? So let's take a look here. Is there sufficient evidence that drug treatment courts reduce recidivism compared with traditional courts at an alpha level of 0.01? So keyword here is reduce. And so we want to have our less than sign here. So that's what we're curious about. Do treatment courts reduce recidivism? So that's why we select that there. And we're all set to go to proceed to step number 3. Selecting our sampling distribution, we know that this, again, right from our very first step before we even got into step number 1, is that we are conducting a 2-sample test for proportions, so we know that this will be a z-test. We have to revisit our question here quickly to see what alpha level is specified, 0.01, and we can revisit here, our friend up here in step number 2, to figure out if this is a one-tailed or a two-tailed test. In this case, unlike question number 1, where we saw the word difference, which signifies both ends of the normal distribution, here we see that we have a direction specified, right? Reduction, less than. That means we are only interested in the negative end of the distribution. You can revisit step 2 here to ensure that you have a direction that's specified. So with that being said, take a look at the chart that was provided in the slides and just take a look at where it intersects for an alpha cutoff of 0.01 for a one-tailed test. And we know this has to be on the negative side because it's a less than question. And that will be negative 2.33. So that serves as our Z critical value or our cutoff point to determine whether or not we land in our safety zone or in our danger zone if we reject the null hypothesis. Okay, as I had mentioned when we were reading this problem right off the bat, I know that I can convert these numbers into proportions really easily. So you see here that we are revisiting our P symbol, which I know a lot of you like to use up here in step 2, but again, you will never use it at the hypothesis stage. So get rid of it, get out of your mind. It's only going to be pi or mu up here. We do use it for the purpose of computation here because we are dealing with samples. Take a look back at both of our PowerPoints for chapter 8. There is a chart on there that shows you the different statistical notations for sample statistics versus population parameters. So if you're having any difficulty distinguishing between the two, I highly encourage you to go revisit that and keep that as a reference as you're moving forward and for the final quiz. So for P1, this is our first group, and we want to figure out the proportion of individuals that reoffended within 1 year if they participated in the drug treatment courts. So we merely have to take 60 and divide that by 275. I have an answer here of 0.2182. I saw a lot of folks at this stage as well round this answer to 0.22. That isn't necessarily wrong in this case, but it will lead to a less precise answer, and you'll see that down below as well. So I encourage you to keep a fairly larger answer in terms of how many decimal places you keep this out to at this stage, only because we will ultimately round our final answer to the hundredth place. But when we're still actually in the computation stage, we want to ensure that we are getting the most precise calculation that we can. And we can always round our very final answer here. But if we start rounding at this stage, the less and less precise these values become as we keep computing it. And so I like to go out 4 decimal places when we're initially computing our proportion values or anything of that nature at this stage. I didn't mark anything wrong because I haven't really gone over that to this point, but just keep that in mind if you ever are in a situation in a future career or anything like that. Different agencies and governments, and I don't know if you work in a law firm and you need statistics on different cases and things of that nature, they're going to want the most precise estimate that you can get. And so just keep that in mind that rounding will change your final answer at the end of the day. And so if you are trying to get the most precise estimate, you will want to keep these numbers as intact as possible before you get to your final estimate. All right. P2 will be the proportion of our group number 2 here. I had 88 individuals out of the 325 who went through the traditional court process who reoffended within 1 year. So that proportion value was 0.2708. And lastly, we just need the sample sizes of each respective group. So that was 275 for group 1 and 325 for group 2. All right. Starting off here, base formula for a 2-sample test for proportions. Here we only needed 4 pieces of information. It looks like a lot, but they really just repeat each other here. And so here is me working through the math. As I mentioned, if you started with just 0.22 here and 0.27, you'll see that it gets a little bit off for you from the numbers I have provided here. Again, I didn't mark that wrong. I may have left you a comment saying, that you may need a more precise answer moving forward, and I'd encourage you to have a more precise answer, but I didn't mark anything for that. But that's why you might have a slightly different Z obtained value down here at the bottom. It won't change the ultimate answer here, which is nice. I think a lot of people ended up around a Z obtained of about -1 point in the high fours, like a 4.9 or a 4.8. And so that's no problem there because, again, it doesn't change our ultimate outcome here. But I'd encourage you to walk through each of these steps, again, showing your work at each subsequent calculation, right? Here, I'm showing right off the bat, this is me just merely plugging in the numbers. Here, I'm showing, right, that I did this calculation in the numerator, this first calculation in the denominator, and then I'm doing the subsequent calculation in this numerator within the denominator and working through each subsequent step. Again, it helps me as the instructor leave you feedback if there's a calculation error that occurs in any of these steps, kind of pinpoint where that occurs. If you jump from here to this very end stage here, but you don't get an answer anywhere close to this, it's very difficult for me to pinpoint where that may have occurred. So please show me your work along the way. I know it's tedious, but that's truly the reason why I do it, is because when I see this and then just a final answer, I don't know what to tell you of where it could have gone wrong because I don't know what steps you utilized in the in-between. So it's really to help me help you. So just keep that in mind. So with this final Z obtained value, we ended up in our safety zone here. So we failed to reject the null hypothesis. We had a one-tailed test with our, I have a little bit of a typo here. This is not the Z obtained. This is our Z critical value. Very important here for our shaded region. So we want to make sure this is our cutoff point between our safety zone and our rejection zone, right? That firm boundary. And so our Z obtained needs to be within our safety zone in order to reject the null hypothesis. And I see it's well within that space for us to be able to do that. So let's interpret the results within the context of the problem. All right, let's revisit what the problem actually was so that we can do that. An example interpretation here is that given that our Z obtained of -1.58, again, yours might differ a little bit depending on how you rounded along the way, does not fall beyond our critical region. So what I'm saying here is that it does not go beyond our Z critical cutoff point of -2.33. We failed to reject the null hypothesis and conclude that drug treatment courts did not significantly reduce the proportion of individuals who recidivated compared to those in traditional courts. So what I'm doing there is not only saying that we failed to reject the null hypothesis, but what that actually meant in context, right? If I just told whoever was in charge of completing this project that we failed to reject the null hypothesis, but didn't actually tell them what that meant, that's not going to be very helpful to them. So again, I want to ensure that I'm giving them the context of what that actually meant. And so in this case, it would be really helpful for them to know, hey, maybe we need to go and revisit the different tactics and procedures and programming we are using in our drug treatment courts, because if we're not having significantly different outcomes in this court that should be more targeted towards individuals who are going through, substance abuse issues, and, we have more targeted programming and things of that nature, and it's not working, we need to figure out something that might work better, right? And that's important information for the state of Illinois to know, right? So we always have to contextualize that back within the context of the problem. Again, here I have both elements, though, within one cohesive answer. You don't want to just provide after your Z obtained here in step 4 that you failed to reject the null, or just say failed to reject in step 5. Interpreting results within the context of the problem is the key element here of step 5. So please keep that in mind. That's where a lot of the errors occur here in step 5. But what you can essentially do is just revisit what the question itself is asking you and just answer it. Is there sufficient evidence that drug treatment courts reduce recidivism compared with traditional courts? Here, we're just answering it. We conclude that drug treatment courts did not significantly reduce the proportion of individuals who recidivated compared to those in traditional courts. We're almost just repeating it verbatim with what the question is. Again, we're not reinventing the wheel. So just revisit what the question is asking and then answer it using the context of both groups. So you'll see here, I mentioned again, group number 1, drug treatment courts. Here, I'm recognizing our alternative hypothesis. It did not, significantly reduce. So we're also acknowledging did not reduce our failure to reject the null hypothesis. And I'm acknowledging that this was a test for proportions. And then lastly, I am also acknowledging group number 2. So we're including all of the elements here of our test that we want to, and it's all within one cohesive sentence. You'll see that I use this essentially base and shelf formula for my response in all of these. So feel free to adopt it. I think it's very helpful to kind of follow the same format for all of these. And like I said, feel free to use it. You don't need to worry about how this might change for each respective question because, again, they follow the same format for almost every single one. So let's move on to question number 3. Nationally, 52% of court cases are resolved within 120 days of filing. After St. Louis City implemented an electronic case management system, a random sample of 150 post-implementation cases shows that 76 were resolved within 120 days. Is there enough evidence to suggest that the proportion of cases resolved in St. Louis is lower than the national rate at an alpha level of 0.10? You must complete the 5-step model of hypothesis testing and show your work to receive full credit. Please round your z-obtain value to the hundredths place. So just as we did for questions 1 and 2, let's first figure out what kind of test we are conducting. The very first word that I see in this question is nationally. And so what that should trigger in your head is, okay, we're probably comparing this to a population. So this is likely a one sample test of some sort. The very second word I see is 52%. Okay, great. Usually when I see a percentage, I know that I can easily convert that back into a proportion, right? All I have to do is divide that value by 100. So 52% goes to 0.52 in terms of a proportion. We can confirm that though by just reading the rest of the question again. Court cases are resolved within 120 days. After they implement that case management system, we take a random sample. Case shows that it's 76 were resolved within that time period. Okay. Is there enough evidence? All right. I only see one other group compared to my national percentage here, and that is St. Louis City. All right. It looks like we satisfied that as well. So my one sample is St. Louis City. They implemented an electronic case management system, and they are trying to compare that to the national percentage. In this case, we convert it to a proportion of cases resolved within 120 days of filing. I also know here that I'm not seeing any words in terms of average or mean, and we said right off the bat with our second word here that we can convert this into a proportion. And so I know that this will be a one sample hypothesis test for proportions. So we're good to go there. And because now we know what type of test we will be conducting, we can move on with our assumptions. Again, these are going to be different depending on the test we conduct. So that's why we have to determine our type of test first. The assumptions for a one sample hypothesis test for proportions are: we are working with an independent random sample. Here I see that is a random sample of 150 post-implementation cases, right? So this is independent of this national figure here. And it was a random sample, so we have satisfied that condition. The variable we are testing is nominal. Okay, let's take a look here. The cases showed that 76 were resolved. This was a little bit of a tricky one that I saw people held up on, so I want to explain this one. Even though you could count the case itself, right? Number of cases might appear to be interval ratio, and it is. That's not exactly what we're looking at here. The variable that we are actually evaluating is whether it was resolved or not. Yes, it was resolved, or no, it was not. It's still being measured in terms of cases, but that's not our actual variable of interest. Again, it's a yes or no binary variable. And so I can see how that tripped some folks up. I do get it. But again, we always want to keep in mind what the variable of interest itself is, not just the variable itself in terms of cases and being able to count those, because that's not what is important here. It's how many were resolved. Yes, this many were resolved, and no, this many were resolved. So at the end of the day, that's what we're concerned with, not just how many cases in terms of count, but just yes and no. So we do satisfy that here in terms of a nominal variable. Lastly, we need to ensure that our sample size exceeds a value of 50 to ensure that our sampling distribution will be normal. I see here that a random sample of 150 post-implementation cases were collected, and so we're above that as well. As I've said in questions 1 and 2, please ensure that both elements here are included. Let's move on to our hypotheses. Again, always with our null hypothesis, our statement of no difference. We will always have our H subscript 0 here with our colon. As I had mentioned, anytime we're working with proportions, it is going to be your population parameter of pi. Do not put a p symbol here. It is not relevant at this stage. Always a population parameter. Right off the bat, we said here nationally, the population percentage is 52%. Converted into a proportion is 0.52. And so that's what we're testing against. Here, for our alternative hypothesis, we also know that this is going to be a pi symbol. Our job here is to just figure out what direction our alternative hypothesis we are testing against is. So let's revisit the research question itself. Is there enough evidence to suggest that the proportion of cases resolved in St. Louis is lower than the national rate at an alpha level of 0.1? Okay, here I see that we have a less than sign, so we are in line with what we see here, right? Is it lower than the national rate? So we're good to go there as well. So just make sure that both of these are in line with each other. That's a good way to double check yourself as well, because in step 3, we want to make sure that all 3 of these are actually going the same way, because if we're off in any direction, that's not good. We need to make sure that all of these are comprehensively in line with one another, because we want to make sure that our alpha cutoff level, particularly if we determine if it's a one-tailed or a two-tailed test, we are determining whether or not we're going in a positive direction, a negative direction, or both. So let's take a look here. Selecting our sampling distribution. Well, we determined right off the bat this is a one sample test for proportions, so a z-test. We also know that this will be an alpha cutoff level of 0.1. We got that from the question up here. And from our hypothesis here with our alternative, we determined that this is a one-tailed test because there is a direction that is specified here in the problem, right? We want to know if it is lower than the national rate. Because of that, we know that this is a one-tailed test. And if you go and take a look at our chart, our alpha cutoff value for 0.1 at a one-tailed test is negative 1.29. Again, we are only interested in the negative end of the distribution because we are only interested in whether it is lower than the national rate. Okay, so that's where you can check yourself here, right? Negative 1.29, lower and lower, right? So all aligned with one another. Okay, step 4, computing our test statistic. Here I have my base formula for a one sample test for proportions in order to get our z obtained value. I only need three values here in order to conduct this problem. The first, here we are with p again, but again, it's because it is our sample proportion, okay? Our sample proportion comes from our random sample of 150 post-implementation cases, and it was 76, right? But again, our hypotheses is coming from 52% nationally. So again, population proportion, now we're working with a sample statistic. So that's why we have P. Again, revisit that chart if you need to. Have it right in front of you as you're working through this. Our sample proportion is 0.5067. Again, if you didn't round out this far, I'd still encourage you. It's going to give you a more precise estimate. I know a lot of folks rounded to 0.51 here. I don't think it actually affected the z obtained all that much in this particular instance, but for future ones, please go out a couple more decimal places. It will have you be in a little bit more of a precise position for future problems. So we have that. We also know that our population parameter for our proportion here is 0.52. We got that from the problem here and what we're testing against. And lastly, what are sample size here? A random sample of 150 cases. So those are the three pieces of information that we need. Again, here's our base formula. I plug that in here, and here is each of the steps of me working through that to finally get a z obtained value of negative 0.33. So with that being said, it's a little cut off here, but we can take a look at our normal distribution down here. Our z critical value is negative 1.29. So that serves as our boundary between our rejection zone and our fail to reject zone. Our z obtained is only negative 0.33. So again, we fell into our safety zone here. And because of that, we failed to reject the null hypothesis. But what does that mean for the context of this problem? Let's take a look. Given that our z obtained of negative 0.33 does not fall beyond our critical region of negative 1.29, and what I mean by that is that we're safe, right? It doesn't go over this region. We failed to reject the null hypothesis and conclude that the proportion of cases resolved in St. Louis within 120 days is not significantly lower than the national rate. So what we're doing there is acknowledging that we failed to reject the null, right? That's what happened down here in our normal distribution. Here's our conclusion within the context of the problem. Proportion of cases, right? This is a one sample case or one sample hypothesis test for proportions rather. And so that's why we only have to acknowledge, St. Louis. Our secondary thing we're testing against is the national rate. And lastly, we want to ensure that we are acknowledging what we tested against. In this case, was our research hypothesis, was it lower or not than the national rate? Because we failed to reject the null hypothesis, we concluded that it is not significantly lower than the national rate. Importantly here, just because we failed to reject the null hypothesis does not mean that this is just different than the national rate, right? Because that's not what we tested here. We only tested lower. So this is the only claim that we are able to make here. So keep in mind that the verbiage you use in your interpretation should match what you have here in your hypothesis and your alternative hypothesis specifically. So keep that in mind as you are working throughout. It needs to be consistent from the problem itself, right? Because it's specified we wanted to know if it was lower than the national rate. So that's what we included in our alternative hypothesis, and that language should remain consistent all the way down to our very last interpretation. All righty, very last question here with question number 4. A prison psychologist wants to test whether time spent in solitary confinement is associated with an increase in reported mental health symptoms. She samples 120 incarcerated individuals who spent at least 30 days in solitary confinement and finds they reported an average of 12.7 symptoms on a standardized checklist with a population standard deviation of 3.8. She also samples 110 incarcerated individuals housed in the general population and finds that they reported an average of 11.2 symptoms with a standard deviation of 3.5. Do incarcerated individuals in solitary confinement report a significantly higher average number of mental health symptoms at an alpha level of 0.05? Again, following our five-step model here below. All right, first determining the type of test we need to conduct here. Let's take a look. All right, we have a prison psychologist, solitary confinement, reported mental health symptoms. First, samples 120 incarcerated individuals who are in solitary confinement. Okay, so this is signaling to me that I have at least one group of interest here, and finds they reported an average of 12.7 symptoms. All right, here's my key word, average, right? Average and mean go together. So that's signaling to me that this will probably be a test for means, but let's keep going. She also samples 110 incarcerated individuals housed in the general population and finds they reported an average of 11.2 symptoms. Okay, that's showing me that there's two distinct groups from one another, right? Those in solitary confinement and those within general population. I see the word average pop up here again. So with that being said, I'm pretty confident that we will be conducting a two-sample test for means. We can also just read this very last section here of the problem itself if we wanted to, check ourselves one last time. So let's go ahead and do that. Do incarcerated individuals in solitary confinement report a significantly higher average number of mental health symptoms at an alpha level of 0.05? Okay. Here I'm resolidifying higher average number, and I have my two distinct groups. So we're good to go with a two-sample test for means. All right, assumptions for a two-sample test for means. Starting off, we are working with independent random samples. So you may have noticed for every single question we have done, this is an assumption that is consistent for every single hypothesis test you will do that involves a normal distribution. So keep that in mind. You can copy and paste it for every single one. Make sure that you include that. Here for means, the variable we are testing is interval ratio. Okay, here, number of symptoms, right? 12.7. And here we have 11.2. So it's the number of symptoms, right? This is something that we can count. It's numerical. There's a distinct difference in numeric distance between them. So we're good to go there as well. And because both of our groups exceed a sample size of 50, the sampling distributions will be normal. So let's take a look at both groups, 120 for group number 1 and 110 for group number 2. So we're good. Again, both elements here need to be included. A distinct assumption that is only here for two sample tests for means is this one right here, the fourth one. The population variances are equal. So if you missed this one, please ensure that you have this written down in your notes. Again, it is exclusive to two sample tests for means, and it will not be a part of any of the other ones that you will see in this course. So make sure to note that here. Hypotheses. Let's take a look at what we're working with here. Alrighty, we are working with means, which also means that we are revisiting our friend mu. Always have our trusty symbol here, H with a subscript of 0 for our null hypothesis. We have mu with our first group here of 1 equals, because it's our statement of no difference, of group 2. So what we are essentially saying here is that there's going to be no difference in the number or average number of mental health symptoms between each group. So those that were in solitary confinement and those that were in the general population. Secondly, H1 designates our alternative hypothesis, and we just need to revisit our question here to see what direction our alternative hypothesis is going to go in. Do incarcerated individuals in solitary confinement report a significantly higher average number of mental health symptoms? Okay, so this is one of our first ones in which we are going to have the greater than sign. So that, is different from what we've tested. A lot of times when we do policy analyses, oftentimes policymakers are looking to see if a treatment reduced something, right? So that's why we've had a lot of examples of that. But in this case, we're looking to see if one group is having disparities against. So are they being mistreated? We need to figure that out in terms of solitary confinement. So that's why we are seeing if it is a greater amount. So that flips for us. We have a greater than sign here. And so make sure that that aligns for you here. You'll also see that change as we get down to our normal distribution here in just a second, because we will be on the positive end of our normal distribution. All right, selecting our sampling distribution. Right off the bat, we established that this is a 2-sample test for mean, so it will be a z-test. Alpha cutoff point was given to us here of 0.05. It is a one-tailed test because we saw here that we have a specified direction of a significantly higher average number of mental health symptoms. And because of that, we need to go and look on our chart to see where we intersect between an alpha cutoff point for a one-tailed test at 0.05, and that will be positive 1.65, right? We're only concerned with the positive end of our distribution because we're only interested in whether or not those individuals in solitary confinement report a significantly higher average number of mental health symptoms, right? Not less than and not different, right? We have our greater than sign here for a reason. So we'll keep that in mind, and you'll see a visual example of this in just a second. All right, computing our test statistic here in step 4. This one's a little bit more involved, arguably the most complicated formula, I would say, in terms of computing our test statistics. So let's go ahead and pull out all the information that we know based on the problem. This is our sample mean for group number 1. Group number 1 is those in solitary confinement. They averaged 12.7 symptoms, so that's what I have here. Group number 2 are those that were in the general population. They experienced 11.2 symptoms. That's what we have here. We have the population standard deviation of group 1 is 3.8. The population standard deviation for group number 2 is 3.5. And lastly, just the sample sizes for each respective group. I have 120 individuals in group 1 and 110 in group number 2. Here is my base formula for a 2-sample test for means in which the standard deviation is known. Had we not known these, and that's beyond the scope of this class, the formula would look different. But again, I'm giving you that information for this. So here is our base formula. Here's me just simply plugging in the numbers. But again, I'm walking through each respective step here as I go along the way. So for the very first one in the numerator, I do 12.7 minus 11.2 to get 1.5. You can say here in the denominator, my first step I took was just squaring those in the numerator, and I go along the way here as well. Again, a lot easier for me to see if there were any calculation errors if I see these steps worked out. You should receive a z obtained value of approximately 3.12. So let's take a look at our normal curve here. Our z critical cutoff point, as we established in step 3, is 1.65. And so knowing from step 4 that our z obtained value is 3.12, I see that we did fall beyond our z critical cutoff point here, so I know that we landed in our rejection zone. What does that mean, though, within the context of this problem? We can say, given that our z obtained of 3.12 falls beyond our critical region of 1.65, right? We are beyond this value here. we reject the null hypothesis and conclude, here's where we're bringing in the context of the problem, that incarcerated individuals who spent at least 30 days in solitary confinement report a significantly higher average number of mental health symptoms compared to incarcerated individuals who are in the general population. Okay? So we're bringing in all of the elements that we have discussed thus far, right? We reject the null hypothesis. We conclude from our first group, right? Incarcerated individuals who spent at least 30 days in solitary confinement. Significantly higher average number of mental health symptoms, right? Because that's what our alternative hypothesis was testing, right? And we had to reject our null hypothesis. And then we are also bringing in what our second group was compared to incarcerated individuals who are in the general population. So not only are we acknowledging both of our groups, right? A two-sample test, we're also acknowledging the fact that this was a mean, higher average number of mental health symptoms, and we're pulling in our ultimate call here that we rejected the null hypothesis. Again, I always find it helpful to plot this out. I would encourage you to do so as well as you move forward on our final quiz, if it is helpful for you, because I think it really helps determine, visually, where did we fall? Are we in our safety zone where we fail to reject the null? Or did we fall into our danger zone and reject the null hypothesis? Again, our key here, though, with step 5 is always to interpret this within the context of the problem. Because if we were to report back, let's go revisit our question here, to this prison psychologist, in whatever prison they might have been in, this is quite alarming, right? Because now we're showing that solitary confinement can have a really adverse impact on individuals' mental health symptoms, right? And if we're trying to keep these folks safe within there and they're experiencing more and more mental health symptoms that could put different prison staff at risk and mental health professionals, that's not something that we want to see. And so that may be something that they could, take into consideration when discussing different policies and directives. And so that's why we need to have this part here. What are we actually reporting back based on the study that we conducted? And so, as I mentioned, that's really what we want to report back. With all of the things we did in steps 1 through 4, we need to make sure that we're actually communicating what the results are. So that's the overall point of step 5. As I have mentioned in many of my announcements and previous videos, I fully recognize that Chapter 8 and hypothesis testing as a whole is by far the most complicated and intricate information that we cover in this class. It is a lot of steps, there's a lot of pitfalls and small mistakes that you can make along the way. Sometimes I still make them myself as I'm creating these questions and trying to come up with examples and doing my answer keys. And so because of that, if you are still having trouble with this information, please email me to set up an appointment or stop by my office hours before you take the final quiz. I really want to make sure that you have a strong understanding of this. Because we've spent so much time on this, it's pretty safe to assume that a good chunk of the final quiz is going to contain problems similar to this. So if you're still struggling after these last 3 problem sets, please reach out because, like I said, they're not really going anywhere for the purpose of this final quiz. So with that being said, please review your individual feedback from this problem set and this answer key review video if you've made it this far. Obviously you have. And if you still have questions, again, please email me. And as always, I will see you in the next video.